Here we go. Thank you, Jason, for slotting me, for moving me up a couple of slots right after James. I see now why you did it. Punishment, I guess. Yeah, so something completely different we're going to talk about today. What I'll be talking about, supposedly, well, at least the title of the talk, something along the lines of simple math for anomaly detection, except that I lied. There's no really simple math for anything. I just wanted to get the abstract through Jason and get into the conference. Because really the reality is that there is very hard. It's very hard to find simple tricks that give you a lot of stuff. And so the first instructional or instructive information you get out of this particular talk is that something sounds too good to be true. It probably is. So there's no simple math. We'll try and keep it a little bit to a certain extent. I won't have put up too much math on up there, but it'll be interesting. Try to keep it as interesting as possible. The other thing is that, for people who have seen my talks before, I usually beat up a lot on things like parametric or Gaussian techniques or supervised learning, all that kind of stuff. And then usually after my talks, people ask, well, it's good that you point out the stuff that doesn't work. Can you please maybe next time talk about stuff that does work? So that's kind of the genesis of this particular talk. Oh, and by the way, I will also still beat up on that stuff, but I'll actually also introduce maybe some things that work a little bit better. And one thing on Adrian and James are absolutely completely right. Listen to them. What's the point of collecting all that data if you can't actually analyze it and actually get useful information out of it? Well, other than like storing it places. Just a couple of real notes. I will show lots of graphs. This is real data. It comes from actually real systems. I won't have any y-axis labels on the charts usually, just because really it doesn't really matter to me what the metric is. It could be unicorns per second. Metrics are metrics. I need to keep reminding myself to slow down. You guys have a role to play here. If I see hands going like this, which is usually the case, means I need to slow down. And then finally, my daughter says, mention cats. Everybody loves cats. If everything else goes wrong, at least there's cats in the presentation, right? Quickly, just a quick note about myself. I'm founder and CTO of Metaphor Software. Was a founder and CTO of a company called Layer 7 Technology, which got acquired by CA. We did a lot of API management and things like that. I actually escaped from CA before the acquisition, so I can roam free and do something else. Before that, I was founder and CTO of a company called Saffron Technology. We did pretty hardcore pattern recognition stuff. Anyway, I've been at this for a very long time. I know I look, I'm actually a lot younger than you think, a lot older than what I look. Interesting thing though, I do want to announce that, for what it's worth, we just last week, Gartner announced that we are a cool vendor, so now in the space, which is really, really cool. I wouldn't announce it here really, but for a data guy like myself, I kind of see there's a trend. So, actually it turns out, somebody pointed out to me that all three of my companies were, cool vendors by Gartner, which is probably an indictment of the low bar used for selection process. But, as a data guy, I'm like, okay, there's a trend here. Let's see if we can keep it going, right? So, be that as it may. So I usually typically start my talks about, sort of the wall of charts. Everybody's been, I don't know how many of you, but I have personally. And it's typically, I think it's company hazing that the new guys usually get shoved in front of the wall of charts and you have to sort of look at that kind of stuff. And if you've seen my talks before, sort of this is where Disaster Girl usually shows up. She shows up at various times during my presentations, but this is usually where she shows up. And the question is like, so what? We've got all these charts. We think we're clever. We're collecting hundreds, thousands, or more of metrics, and we say, all right, we're going to pick 5 of them, right? Or 10 of them if we're good, and put them up on a chart, and then watch them. What the hell are we doing? It's really, really meaningless. So what the side effect of the wall of charts is alert fatigue. And the great line here from John, he's probably not around today, but alert fatigue is the single biggest problem we have right now. We need to be more intelligent about alerts, or we'll all go insane. And this is sort of where the theme of today's talk really is: how do we actually deal with that kind of stuff? Because watching screens doesn't scale, really. And it's actually useless. Like, how many screens are you going to watch before you just go, flatline, right? And, you could hire a whole bunch of people and sit and, fill out the sweatshop kids, a whole warehouse of kids watching screens, but really it's not a good way to do it. We got to turn things over to the machines. Now, I originally thought this reference, you guys might all be too young for this reference, but somebody has used the monolith in a presentation before me, so I feel a little bit better about that reference. So really, we got to turn things over to the machines and have them do the grunt work. We use computers to do grunt work and a lot of other things. Why not use them to actually, quote unquote, watch screens for us, right? And actually give us some useful information. So to the rescue here, this concept of anomaly detection, ta-da, that's been around for a very, very long time in other fields. We think of anomaly detection or outlier detection, search for events or items that do not conform to our expectations, right? For us, really, it's, for me at least, I shouldn't say for us, I shouldn't speak for everybody. For me, really, it's about looking at stuff, metrics that goes wonky, right? As soon as something goes wonky, I need to know about it as soon as possible, right? And that's what anomaly detection techniques are about. So then we said, all right, we're going to turn things over to the machines. We're going to do automated stuff. We're going to do all that kind of stuff. Where can we, let's look around because we're smart people. We don't want to reinvent the wheel. So let's look around and see who else is doing this anomaly detection stuff. And the first thing that we notice is that, these manufacturing guys are pretty smart. They've been doing it for quite some time. And whenever they process flux capacitors or whatever it is that they do, they're stamping them out. And they actually kind of reject the ones that are quote unquote outliers, right? And so they measure the diameter, the weight, the thingy-majig about their flux capacitors. And they keep measuring them. And then if something goes outside of this line, they figure out, they actually throw them out, right? So this is great. We take a look at it and actually, to understand what's going on here is that they make assumptions about probability distribution and the behavior of the processes that they're doing. And these assumptions is that the data that they're dealing with, the circumference or weight of the flux capacitors, is normally distributed in the Gaussian. You guys all know the bell curve, right? It's sort of normally distributed with a useful mean and standard deviation and so on. And the other major assumption that they make is that the data is probabilistically what's called stationary, in that means it's mean, sorry, see what I did? It means that it's mean, haha. Oh no, I'm clever, is kind of stationary in that it doesn't change that much. Its standard deviation doesn't change that much, and its autocorrelation doesn't change that much. So I can look at it in the future, look at it in the past, and it's got pretty much the same kind of shape around that. So when I have data that looks like that, everybody's heard of the 3 sigma rule. Everybody nod, please. Okay, good. Which means, so the 3 sigma rules means that 68%, so if you look at a mean and standard deviation, typically in the bell curve, 68% of the values lie within 1 standard deviation of the mean, 95% of the values lie within the 2 standard deviation, and 99.73% of the values lie within 3 standard deviations of the mean. So these guys are the outliers. So we say, all right, it's great, that's awesome, we're going to do that. And that kind of explains these mysterious red lines that we see on these graphs. That's what they are. They figure out there's a mean somewhere, and then most of the good stuff's going to lie within 3 standard deviations, 3 sigmas, and then anything outside of that is going to be the outlier. So we say it's great, perfect, we're going to use it. And the important thing about that is that standard Gaussian distributions are powerful because anytime I can make the same prediction because the statistical properties of data haven't really changed. So I can say, what it was last week is going to be the same today, it's going to be next week, so I can make comparisons. And even if I have 2 different kinds of processes, I'm measuring, I don't know, flux capacitor and torque converters, whatever it is, and if they have the same kind of distribution, I can actually correlate them and measure them together, so that's really great. So let's do this, guys, all right? So we're going to do it. We're going to actually apply these principles that have been working for decades and decades and decades to our stuff. And then we do it, and there's no dramatic music. Can you cue in some? Okay, all right. Ta-da, everybody. And then, then this happens, right? So we've got this kind of data. You've all seen the same data. Don't tell me you haven't seen this data before. It's all the same. And this happens. We apply 3 sigma, and we are woken up at 2 a.m., at 3 a.m., at 4:55 a.m., and 7 a.m., and so on, right? And we're like, oh, what's going on here? So, or actually worse, something like this happens, right? Again, do not tell me you haven't seen this graph before, where we're woken up maybe once or twice, and then something bad happened, and we're never woken up, right? And this is actually worse, right, in my opinion. But they're both bad, right? And like, you know, fuck, what happened? What gives, you know, the stuff, people have been using that stuff for ages, why doesn't it work for me? And, you know, the reality is that, remember this? We made major assumptions about the statistical distribution of the data, right? That it's Gaussian, it's stationary, and things like that, and where in fact it doesn't. So for that first diagram, where we got woken up, you know, every half hour by an alert, this is what the actual distribution looks like. It looks nothing like a bell curve. And for the other one, this is what it looks like, right? So an important lesson here is that most of the data that comes out of your data centers is not Gaussian and it's not stationary, right? So you gotta stop thinking about using all these kind of techniques because they will not work. I can guarantee you that. So we say, all right, you know, this is not good, we need to do something better, right? So then we start looking at other stuff, say, all right, these static thresholds are ineffective on this kind of dynamic data because they use the mean as a predictor, right? So we're actually looking at the mean, and then we look at 3 sigma on each side of the mean, right? So that mean is not maybe a good predictor. Let's look at something that's a little bit more dynamic. If our data is moving, let's maybe look at some kind of moving mean with some kind of moving thresholds, right, that accommodate new data and new values. Smart idea. Say, all right, that's great, let's do this. So this is where the concept of moving average came out. So we look at any point in time, you know, your next value should not significantly deviate from the general trend of your data, right? In a well-behaved time series, you know, the expectation is typically that if you have a value, the next value should be kind of relatively consistent with the trend, right? So the mean as a predictor is too static because it relies on too much past data. It's static. It looks at all the data and puts a static mean. So what we want is, instead of an overall mean, we want to use the finite window of past values. So just look at windows, and then say, all right, I'm not going to look at the whole history of my data because it's changing. I'm going to look at just a particular window and average that out, look at the mean of that, and then slide the window, look at the mean of that, and slide the window, look at the mean of that, right? So then the alert, if the actual value significantly deviates from the predicted value. I'll say, all right, this sounds like a lot of fun, sounds like something that's doable. So then typically what we end up doing in moving average is we smooth the data through that sliding window. And then we compare the squared error rates between the smooth data and the actual data. And then we want a new form of standard deviation, so we can measure 3 standard deviation away. So we actually smooth that error, and then we get this kind of new improved computed standard deviation. And then we do the same thing. So all right, we're on a moving threshold that moves with the data, right? That is 3 new squared error-based standard deviations away from that moving mean. Right, ta-da, it's great, we're gonna do it. So there's tons of ways to do this. And I'm going to go through a couple of them, mainly because I just want to sort of show you the ridiculous amounts we go to try and fix that stuff when it actually, you know, and the results. So we start with a simple moving average. Say, all right, you choose a window of n values, right? I'm gonna average these n values, and that's my new value, right? Then I move by 1 point, new window, new value, average that, and so on, and so on, and so on, right? So that's the typical moving average. So each value in the window contributes equally to that prediction. Then, you know, people said, well, wait a second, what happens if I have spikes or I have outliers in that particular window? That's going to skew the whole window, right? So, okay, you know, we're going to do something even better. We're actually going to have a weighted moving average, so that instead of using each point in that window contributing equally to the average, I'm going, the points that are sort of more in the past contribute weight. So I weigh them. You know, I put a little bit more weight, less weight on the ones in the past, and so on, right? So then we have issues here because, you know, again, that doesn't work as well. So we say, all right, we're going to actually do it a little bit better. We're going to have exponential smoothing, right? So then the trend in the line goes less and less and less. So the past points contribute less and less and less. Then we figure out that actually it doesn't deal with trends in the data. So like, shoot, we're going to do double exponential smoothing, right? Now, all right, you know, we've done double exponential smoothing. You know, finally we've dealt with trending, and then, but wait a second, It doesn't deal with seasonality. All right, triple exponential smoothing, right? You see, sort of, I'm only listing these things to illustrate the length we go to try and fix something when fundamentally it is broken, right? So let's look at another example. That same data where we were woken up all the time using just a static threshold. We use something really, really sophisticated called whole winters, which probably you've probably heard of, right? And this is, so just as an illustration, this is the whole winters smooth data that we get from a sliding window. This is the raw data. The blue is, sliding the window using triple exponential smoothing. And then we've computed the square error, and the red is the 3 sigma standard deviation of the squared error between that and the actual raw data, right? And so, shit, we're still getting woken up all over the place. Less though, although it doesn't look like because I use big red dots, but if you counted them, which I did, you're woken up a lot less, right? Which is, fair. So I'm not 2 and 3 and 455, maybe at 2 and then 6 and 1, but it still, doesn't work as well. Then now for the other thing, for this particular example, I'm woken up all over the place. So it went to worse, right? So again, there's issues there. And problem is, so the question is, are we doomed? Like, why doesn't this stuff work? And the reality is that all that stuff that you hear about, you read about, you download all kinds of tools to play with, exponential smoothing, whole winters, what have you, all that kind of stuff, really works best on data that is normally distributed in Gaussian. Even some of that works kind of okay on data that is not normally distributed, as long as the deviations are normally distributed. And I can tell you, having looked at reams and reams and reams, 80 gajillions points of data, that most of the stuff that you're going to get out of your data center is probably not normally distributed, or at least the deviations are not. So that kind of stuff, they're not. But on the other hand, we're not doomed. This is usually where I stop, and I start beating up a lot more on other stuff. But I decided to be nice this time and actually talk about stuff that maybe actually works, right? So there's lots and lots of other non-Gaussian based techniques. I can only scratch the surface, in this talk. Unless you want me to stay during lunch, and we don't have lunch, and I'm open to do that, right? So the first trick, so I'm going to introduce 3 different tricks. I call them tricks. First one is the histogram. I would much prefer if you did like kernel densities or things like that, but I said simple, so a histogram will work relatively well. You've got 3 time series here. What are you going to do with them? This is normal. It's easy, like hist, open bracket, x, comma, 50, bin, close bracket, and that's it. One command in R or MATLAB or Octave, whatever, you'll get something like that, which is a lot more useful than the time series up, right? You don't get any information out of that one on top, but you get a lot of information out of this. Say, all right, you know what? It's actually relatively bell-shaped. It's probably normally distributed. So now I can do a little bit more analysis on it, and maybe the 3 sigma stuff or whole winters will actually work, right? I look at other stuff, this isn't normally distributed. It's very, very easy and simple thing to do, and almost nobody does it, Just take a look at the distribution of your data. This certainly isn't, right? So then you can spend hours, days, weeks, or more. I've heard people have come to me after talks said, we spent the last 2 months implementing whole winters on our stuff, and it's still not working. And I said, have you spent 5 minutes looking at the distribution of your data? No, right? So that's really, really important. Just take a look at the data, understand what it looks like first, before you rush headlong into doing some kind of analysis, right? So that's trick number 2. Trick number 2 is the Kolmogorov-Smirnov test, and I only mention it because I like saying it. The other reason I mention it is that it sounds cool. We'd be like, hey dude, and then I was there, we were at the party, and somebody walks by, you want to impress, you say, and we tried the Kolmogorov-Smirnov test, It's pretty cool. But actually, the funny thing about it is it actually works. So KS actually is used to compare 2 probability distributions. And it makes absolutely no assumption whatsoever about the fundamental, whether the distribution is Gaussian or not. No assumption at all about the distribution of the samples. So the thing about it actually is used to compare, not actual distribution, but cumulative distribution. In essence, it's the integral under the distribution curve, so it'll always end up being between 0 and 1, right? As you integrate your distribution of the samples, right, it's going to go from 0 to 1. So it makes absolutely no assumptions. It measures the maximum distance, the L2 distance between two cumulative distributions. So you've got here two different cumulative distributions, and that's the maximum distance between them. And you can actually make some kind of test and hypotheses about like p-tests or what have you about what it looks like, whether these samples are similar or not based on that distance. It can be used very, very well. Actually, it's extremely effective, and I'll show you an example. When used to compare periodic or seasonal data, so day to day, week to week, or so on, right? So KS works really, really well. So the most effective way to use KS is to look at windowing. So again, I know this happens around Christmas time, right? So that's why here, but ignore this. It could be any time, right? So I'll pick windows of the same period week over week, right? So for example, with KS, I want to compare, every Monday or every Wednesday or every Thursday to every other Thursday. So I'll pick this window, and this window. So first I want to compare this window to this window and see what the KS does. And then I'll compare this window to that window and see what KS gives me, right? I don't want to do it week over week over week or what have you, right? Or as a sliding window, right? So if I compute this is the data, the raw data from those first two, if I look up. So this is the superimposed data from this window and this window, right? So this is what the data looks like. To me, by eye, it looks kind of similar. But you've got 5,000 of these things. You can't have 5,000 screens, 5,000 people watching them. That's why you got to let the machines do it. And this is what their cumulative distribution look like and over that window. And so this is what actually the distance looks like, right? Which is good. Now, this is the data from that Christmas day and the data from the exact same day a week before, right? Again, by eye, it looks different, but we don't want to be watching things. And this is what the CDF looks like between those two things, right? And the maximum distance is pretty high. So then, if I use KS, that kind of test, and I start measuring windows and sliding, point by point or window by window, day by day, hour by hour, whatever, however you want to do it, right, over that time, and start computing that maximum distance between CDFs, right, I will get a graph that looks like this, right? So there's no data here because it takes a little bit of time to accumulate enough data. I'll get a graph that looks like this, and then I can use a p-test or any kind of simple statistical techniques to put some kind of threshold on it, and then all of a sudden, wham, I'm starting to get something very, very useful, right? So that's So that's something really interesting and really fun and relatively, sorry, fun for me maybe, relatively simple that you can actually use. You can start looking at stuff like that to do things. The third trick that I'm going to present is diffing or derivatives, right? So a lot of the time, not always, so don't say, hey, Touf said, it's always and it's not working. A lot of the times, even if your data itself is not stationary, its derivative is. It's an interesting little factoid because a lot of data comes from what's called random walks. If you look at the difference between one point and the next point in the time series, you look at the differences, they're usually relatively randomly distributed, right? So most frequently, the first difference is sufficient. So I can create a new time series, difference of S, which is, S at time plus 1 minus S at time t. So actually what you're really doing is taking the time series itself and then shifting it by 1 point and then diffing the two, right? And that's what's called first difference, right? And the first difference actually a lot of the time ends up being relatively stationary and relatively well behaved from a Gaussian perspective, right? So then having that, I can actually perform some useful Gaussian-based analytics on that difference itself and then relate back to the original series. So again, and an example here, this is again real data from one of our users. This is what it looks like. The probability distribution function is all over the place. There's no Gaussian at all in it. But if we do a first difference of it, all of a sudden, it looks a lot more like something you can actually, that's manageable. You can actually do some real statistics on, right? So again, an interesting technique that you can use. I'm kind of, yeah. So I think I kind of, that's all I wanted to talk about today, because then anything I can go, any more I introduce is going to take another like 45 minutes to an hour. At this point, I think this is all I can talk about. The lessons is that, we're not doomed, but really, really important to know your data. You need to understand the statistical properties of your data, where it comes from, what it looks like, and things like that, so you can analyze you can realize what kind of analytics to use. Your data is as important as actually people have said before me. It's funny, that we're all saying the same thing. You spend time collecting it, so spend time analyzing it. The other important thing is that a large amount of data, standard data, is actually non-Gaussian. So don't use Gaussian statistics on it because they won't work. You're going to spend a lot of time. You're going to waste a lot of time. Use the appropriate techniques. So I'm here for the rest of the conference. Sorry, we couldn't get into much more depth or details because, like I said, I had to make a decision as to whether to go another hour or not. But I want to talk a lot more about algorithms, what have you, whatever you guys want to talk about or ask me. Come talk to me or email me. You can find me on email, on Twitter, anything like that. And of course, I have to do this. And we're hiring. Right? So come talk to me if you want to move to beautiful Vancouver, British Columbia. That's all I have for now. Any questions before lunch?
Damn it.
No. That's only one. Sorry, the question was, is my point that we have to get things into Gaussian form so we can analyze them? And the answer is no, actually. I'm sorry if I conveyed that message. KS, for example, does not rely and KS is pretty effective technique and does not rely on any kind of Gaussian distribution. Matter of fact, does not rely on any kind of particular distribution. The only reason I mentioned trick number 3, diffing, is that sometimes you want to look at the differences between, at the derivative of your time series, so you can analyze, so you can figure out if it's a random walk or not. And if you effectively do the diffing, and the diffing comes out to be Gaussian, it tells you a lot about your time series. It tells you in essence that it's a random walk. So there's a very, very good established statistical technique that you can use on random walk time series, even if the original time series itself is not Gaussian. So that's the point of that trick number 3. Does that help clarify? Okay.
All right, thanks again.
Oh, thank you. Thanks.
Thanks again to Toufic.